Good afternoon. My name is Simran Maurya with the Energy Management Association, and I'd like to welcome you to today's webinar and thank Energy Twin for sponsoring today's session. A few items before we get started. Presenters will be holding the questions until the end of the presentation, but we encourage you to submit them at any time using the Q&A button. If you happen to be experiencing technical problems during the webinar, please use the Q&A button to inform the panelists, and our producer, William, will assist you. This presentation is being recorded and will be available for viewing within a week. In terms of the continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. And finally, if you are a certified EMP, your CEUs for attending this webinar will be automatically uploaded to your portal after the webinar concludes. Today's webinar is Finding Black Sheep in Your Building Portfolio Using Explainable AI. Our speakers are Široký with Energy Twin, a machine learning solution for energy consumption analysis, and Allison Fitzpatrick with ACTuate Facility Technologies, a clean energy tech company delivering energy efficiency and resource optimization solutions to small and mid-sized buildings. I'll hand it off to our panelists now to introduce themselves. Han, take it over.
Okay, thank you, Shimmer, for a kind introduction. And I am Široký. I am CEO and founder of Energy Twin, and I will handle the first part of the presentation. Since I am involved in research and development, I will talk about these topics related to AI in energy sector with special attention to explainable AI. And then Allison will take over and she will focus on some real-world application of these principles in fast food restaurants. Let's start with AI in energy sector in general. There are different ways how AI could be utilized in energy sector. A lot of these things are related to grid and its optimization, or from the customer side, demand response, like adjusting to some time varying prices of electricity, etc. There are different things that could be where AI can help energy trading. There are amazing algorithms and quite a lot of progress here. Of course, AI is heavily used in predictive maintenance, but today we will focus on energy efficiency in this webinar, and we will mainly focus on analysis of electrical energy data. We all see some kind of AI hype in these days, especially, and sometimes it may be seen as kind of magic solution, silver bullet solution, but it could lead some unrealistic expectations. And I want to focus on large language models in particular, because a lot of times I hear something like, hey, it's why we just do not use ChatGPT, just upload the data and ask for insight, and that's it. And I do understand why people are thinking this, and I can demonstrate it on this real world example. This is just a few days ago when I created this prompt where I uploaded a CSV with electrical energy data and asked ChatGPT to create a random forest model and provide me a prediction with time series chart. And this is what I get. Actually, yeah, nothing else was there. So really amazing. What you can see is a chart with blue is the measurement and the orange is the prediction provided by this model that was identified somewhere underneath in ChatGPT. So one may ask, this is it. So you will see some charts in the presentation that will look very similar. And what is the difference? So why we need to take care of all these things? Why we do not just use this? And I want to address this question in this presentation. And let me start with this overall table that somehow tries to summarize some of the challenges that you may face when working with data and trying to deliver some AI insights. So first of all, let's focus on data quality and pre-processing issues. In general, you may face these challenges like outliers in your data, missing data, some scaling factors. But especially in energy sector, since we are working with time series, there is a lot of things that can go wrong with date time, like formatting, like handling time zones. And if you get it right, you definitely hit daylight savings. So yeah, one day in a year has 24 hours and stuff like that. Or you may struggle with conversion between KWH and KW. It works nicely if you have good data, but if you have some errors in reading, you may spend days on these issues. But we will not handle this in today's presentation. We like pre-processing, we will focus on modeling. So again, in general, there are two, or let's say there are many things that could be discussed, but I just want to point out two of these: overfitting and underfitting. What does it say? Overfitting is a situation when you have too complex model, there are too many parameters in your model, and it works perfectly well for the training data, but it lacks the ability to generalize the underlying physics or relations in the data, and therefore it does not provide a good prediction. Actually, this will be almost sure for the random forest example from the previous slide. It will not be able to generalize, and it will not work properly for the data that has not been included in the training set. On the other side is underfitting. It means like you have too simplistic model, and it does not provide the required level of insight. And yeah, a nice example could be using monthly model when having 15-minute data. So it will not provide any insight into what's happening within a day or within each hour of that period that you are analyzing. So both of them are bad, and you need to find out a good compromise between the complexity of the model and not hit overfitting. And again, in energy sector, there are some specific challenges. First of all are these seasonal and cyclic patterns, like seasons of the year, or patterns within if it is an office building, there is completely different regime during the work days and during the weekend. And this is something that we will focus on in this presentation. And you also have a lot of external factors that do influence this energy consumption of a building. Like, yeah, there are some occupants that do have some impact on consumption. Weather definitely influences the energy consumption, and there could be some events like unscheduled events or some holidays, etc. So all of these things need to be somehow handled in order to have a good model. Before we jump in, let me stop for a while on energy data granularity, since it's quite important point. Usually you may have utility bills, but they are with monthly granularity, providing very limited insight. We will not talk about that today. If you have utility smart meter, you may have daily data, usually when using heat or gas, but for electrical energy consumption, you probably will have 15 minutes data or hourly data, and this is what we will be focusing today. In the title of the presentation is this Explainable AI, and I would like to dedicate the next slides to this topic and illustrate what's behind this. I would start with this explanation of drawbacks of non-explainable AI. On the right side of this slide is an example of neural network parameters, actually neuron weights, and if you have a feeling that you are lost in this matrix of numbers, you're not the only one. Actually, what you can do if you're missing some feature in your model, like it fails in predicting weekends properly, or it handles temperature prediction badly. How you can tune these parameters? Basically, you cannot. You just need to, since it's a kind of black box model, you just can change the structure of the neural network, like adding more layers or more neurons, and try to identify it once again. Actually, again, this will be properly true that it will not handle weekends properly and give bad high temperature predictions for the example from the large language models. And it will be also true that in this random forest, you do not have these parameters that could be easily tuned, since there are hundreds of random trees, decision trees. Sorry. And explainable AI provides some insight. Actually, it focuses on explaining relation between inputs and outputs. There are other aspects of explainable AI, but we will focus mainly on this, being able to see this relation and use it in practice in this energy sector. Since we will talk about electrical energy data, interval data, I will talk mainly about this TOWT model. TOWT stands for time of week and temperature, and it was introduced by Lawrence Berkeley National Laboratory in this paper. And since then, it's it became a standard, let's say, and actually it's implemented in these two open source packages. So you can try download them and play around. They have, especially in Open Meter in CodeTrack, you can find a lot of useful information, and yeah, it's easy way how to jump in. What is important about TOWT? This model provides decomposition of interval data into two basic elements, and it's a weather-dependent load and time-dependent load. And let me explain this using this analogy, this orchestra. Actually, orchestra consists of different instruments with different tempos, sounds, and so on. And for unexperienced listener as me, it's just harmonious sound. But for experienced listeners, it's a composition of different instruments, and they are able to decompose this harmonious sounds into different instruments and understand this. And this is exactly what TOWT provides here, like this decomposition of different overlapping influences in this energy data. In this presentation, all the examples will be based on the energy twin model that we are using, and it's based on the TOWT with some improvements that we introduced over the years. I will not go into all the details of these, but just to introduce some of these, like there is more complex handling of weekends and holidays in special. There could be another input variables, not only temperature, but others like solar irradiance, wind, occupancy, etc. And since we are using constraints, it's based on quadratic programming instead of ordinary squares. I'm grateful that we have been able to collaborate on that with the Czech Technical University in Prague. And also thanks to this collaboration, we have been able to test it on thousands of publicly and private data sets. Okay, I will focus now on weather dependency, since it nicely illustrates this, these features of explainable AI and these advantages that it provides. What is the common approach? Here are the data from an office building, and in the top chart, the blue, and in the bottom chart, the orange is outdoor temperature in degrees Celsius. And what you can say about this is like there is some increase in the energy consumption during the summer night, summer months, probably due to hot weather. So there is some cooling related energy consumption. But yeah, it's just a general phrase and no insight. So let's dive in. And what you can do is, like, you can draw this scatter plot. On the x-axis, the same data, and on the x-axis is outdoor air temperature. On the y-axis is energy consumption in kW. And let's try to read this chart. So, and each circle is 1 hour. The top cloud of points are probably hours when the building is occupied. The bottom cloud of points could be related to unoccupied hours. So some insight is here, but let me ask a question. What is the expected energy consumption when outdoor air temperature is 25 degrees? And the answer is not helping, because it could be something between 60 and 140 kW. So it does not help much. And you may ask, is there some way how to automatically quantify this relation between energy consumption and weather? And this is how it's handled by this model. And this weather dependency, this is visualization of one part of the model. And this weather dependent part is the portion of energy consumption that fluctuates with weather. So, and the red line is related to the time when the building is occupied, while the blue line is related to times when the building is unoccupied. And if we ask what is the expected consumption when outdoor air temperature is 25 degrees, the answer is simple. It's 12 kW plus this time dependent load. So due to the weather, we can add 12 kW for 25 degrees Celsius outside air temperature. Let's focus on this time-dependent load. It's, as its name says, a portion of the energy that fluctuates with time of week. And we can ask, for example, what is the expected consumption at Friday, 3 p.m.? And it's some part that weather-dependent load plus 87 kW here. And now we just combine these two things. And if we want to know what is the energy consumption at Friday, 3 p.m. with outside at temperature 25 degrees Celsius, we just combine these two and we have this answer. It should be something like 99 kW. And you may see that for the morning hours, it will be higher. There will be lower energy consumption during the lunch, etc. So you may think about all these combinations of time of week and temperature, and you may actually visualize this in this cool 3D chart, where on one axis you have hour of week. On the second axis is the outdoor air temperature, and on the z-axis is the expected power consumption. So again, this example with Friday 3 p.m. and outdoor air temperature 25 degrees Celsius, we see that it also says like this 99 kW. Actually, this 3D chart is useless. It just looks cool and nicely visualizes what's behind this. So far, we focused on the description of the model and how it's built. But since we are in the energy sector, let's focus on analysis. What does it says about the building consumption? How to read this? Again, we are back in this weather dependency, and let's interpret now these data. So first of all, we see that during the cold temperatures, there is almost no increase in the energy consumption. So we can say that there is no or very, very low neglectable heating, electrical heating. But we see very, very sharp increase in the energy consumption with hot temperatures. it's like 100 degrees Fahrenheit, where we see the arrow, and there's almost 40 kW for cooling. So we can interpret this: is this relevant with respect to the installed cooling power, yes or not? And most importantly, we see that this blue line is not increasing. What does it mean? They are not cooling during unoccupied hours, which is perfect. But it's not always the case. And yeah, I want to emphasize that all this insight is provided just based on the main meter. You can draw these charts if you deploy multiple sub-meters for cooling system, for heating system. You can do that. But this is all just gained. This insight is gained just by analyzing main meter from the building, correlating this weather data and regime of the building. But as I said, it does not always look like this. So on the left side is another example of very nice, we call it cooling setback. So very nice cooling setback. But on the right side is an example of a building that definitely has some significant cooling during weekend. And let's focus on this example on the right side. So you see that in the maximum, this 100%, it's related to something almost 350 kW, and during the unoccupied hours, it goes to 80% of that. So we say that cooling setback is something like 80%, and you may guess that this is not ideal, that during the weekend when the building is unoccupied, they do not need so much cooling, and it could be lower. And based on the hundreds of similar buildings we analyzed, we usually used this industrial standard, like cooling setback should be 30% at most. It's not a general number applicable to all buildings, but for this particular example, it's very relevant. And we may ask, how much energy could be saved when reducing cooling to this industrial standard? And this is what I really like is since we have this model of a building, we can simulate that. So there is a blue and red chart. Actually, during the working days, these charts are overlapping, but during the weekend, we see that original is higher than the blue one is higher than the red one. That's the simulation, indicating that how it will look if we will be able to reduce the cooling setback from 80 to 30%. You may see that there is still significant portion of energy related to this time-dependent load. But since we are able to decompose it to time-dependent and weather-dependent, we may play around with this weather-dependent and have this quite a specific simulation and have these numbers like actual cooling setback ratio is 80%, and estimated savings in this particular building are 88 megawatts per megawatt hours per year. So this provides us this whole year simulation. And actually, this is a very nice example of something that's usually denoted as digital twin, when you have this digital twin of your building. And one of the cool things you may do with that is to make some if-then simulations that cannot be done in practice, but you can easily tune some of these parameters and see the effect. So this is a nice example of that. But so far, we have focused on one particular building, and having a lot of energy data, we have been able to summarize the whole data set into these two parameters. So what is the actual cooling setback ratio, and what are the annual savings? And this is all thanks to this explainable AI. You will not get this from some black box model, or it definitely would not be as straightforward as this procedure. And the most important part of it is if you have a portfolio of buildings, and you may turn these into KPIs, into metrics, how to compare these buildings. And this is anonymized set of buildings, but based on some real world data. And there are different KPIs, and in the red rectangle are highlighted these cooling setback ratios. In the first column are these percentages that you have seen, and in the second column, in this red rectangle, are estimated annual savings. And it's as simple as this, like just sort them according to cooling setback. And yeah, here are the black sheep standing out of the crowd, and you may focus on them and try to find out what is behind this and investigate them. And actually, this is quite an important point, because it's a really powerful table with a lot of information in that, and it's provided thanks to this explainable AI. But there is a role of a human, of expert, to investigate what's behind this. And this is the place when human will not be replaced by AI. Because yeah, there could be some reason, like there was a technician, but he retired, and yeah, it just went wrong. And yeah, this is something where you really need some human touch in investigating this. But energy expert will apply their knowledge here at the best, instead of, I don't know, fighting with Excel and working with interval data in Excel and trying to make some conclusion out of it. And last remark here is that I've been using this cooling setback ratio as an example of some KPI or metric that could be derived. But this is not the main message. It's not about the setback ratio. It's about the fact that using Explainable AI, you can derive some KPIs and then work with them. Like if you there are different like heating setback or different KPIs in this table, but you can define your own. For example, we are focusing on some KPIs that are related to start of your office hours, how well is aligned the energy consumption with expected schedule, etc. So you can derive different KPIs, and especially if you have a portfolio of buildings, it's extremely powerful, because you just sort according to one, handle these black sheep, and once you're done, you move to another KPI, and yeah, you have again few black sheep to deal with. So I would like to hand it to Allison, and she will provide some interesting examples from fast food restaurants.
Yeah, thank you. So Jan gave some really nice examples of how these tools and these AI explainable models can be utilized to determine when there's problems with setbacks within a facility. But those aren't the only things that we can utilize these tools for. And so going into some examples of a portfolio of buildings that was fast food restaurants, the first thing that I want to talk about is energy savings evaluations. So measurement and verification. So you have decided to make some improvements that should save energy within the building, and you want to measure what the impact of those energy improvements are. For those of you that are measurement and verification professionals, this chart may look very familiar to you, but we'll walk through what exactly it represents. There's two different time periods here. On the left-hand side, we have your baseline time period, and that is the time period before you make any energy conservation changes. So before you implement those measures. And that is really the time period that you're going to utilize to create these explainable AI models. And you'll use that time period to train the machine learning model. And then after you implement your energy conservation measures, you expect some savings. Your model now is still going to predict what the energy usage of that building would have been. You still have that digital twin that says, under these particular conditions, at this time of day and at this temperature, this is what this facility energy usage should have been. But during this evaluation period now, after your implementation of your measures, you also have your measured energy, which should be much less. And that's represented by your green line on the right side of this chart. And so now when you compare your blue line, that is your predicted energy from the model, and your measured energy on your green line, the difference between those two lines is your savings. And we can see this in a real world example on the next slide. So this is a single fast food facility. And the left side of this graph represents the baseline period. The bottom left, you can see, again, this prediction in blue. That's what the model is saying the energy use should be in that facility. And your measured is in red. Before you implement measures during that baseline period, the difference between your predicted model and your actual measurement is very close to zero. And you can see that in the top left quadrant of this chart, where your accumulated difference is zero. Now, the moment, the black line in the center, that's the moment where energy conservation measures were deployed in this particular facility. And you can immediately see in the top right quadrant that the difference between your model, your predicted model, and what actually is measured starts to go down quite rapidly. And then visually, you can also see that in the model where your prediction is higher than what's measured. The nice thing about these tools is not only can you visualize them, but we can also use these tools to really quantify what the energy savings is across whatever time period you want to analyze. That difference between your predicted and your actual measurement becomes your savings, and it becomes quite easy to calculate at that point. Now, I know that some of you are saying, man, I would love to be able to do this, but we don't have good baseline data. It's one of the challenges in our industry. And so if you don't have that baseline data, you can still utilize these tools. Say you implemented an energy conservation measure a year ago and you didn't have data before, you can still utilize these modeling tools. Instead of creating a model based on baseline data, we can create these explainable AI models using data with a piece of equipment or a whole facility performing as you would want it to, right? And now this becomes a key performance indicator. Are we continuing to perform at the same level that we have in the past at this target energy performance? And the same models can now really betray, in this case, this is an example of an HVAC system. So this is sub-meter data rather than whole facility data. But it really starts to betray that over a year, this equipment was performing very well. Your difference between your prediction in the model and what you've measured is close to zero. And then sometime in July on the second year, the energy use, now your measured energy use is greater than your prediction. And so that's an immediate flag that you have a problem. In the energy sector, we all know we're never done. There's no such thing as set it and forget it. Buildings are interactive things, right? And so we all know that monitoring these things can really allow for faster action. But I want to go deeper into these models now, because it's when we get into not the daily use as we're looking at here, summed up, but we really start to look at these models that are using 15-minute data or hourly data that start to tell us more about what could be going on now that our energy usage is gone up. And so this same HVAC system, if we look not only at a year and a half of data, but we take just a week of data during this time period where it's not performing well, now we start to look and see throughout the course of a day, when is it not using energy properly? And the model will tell us this too. And so we can see this particular facility, this is an HVAC energy usage. And so overnight, you can see that there are some setbacks. And in fact, we can see that the prediction in blue of what the model says it's going to use, this HVAC system, is actually greater than what's measured. And so the setbacks on this HVAC system are better than they were when we created this model, right? So they've done better overall performing overnight with their setbacks. But if we look at the time period during the day, during occupied hours, now we can see that the measurement in red is significantly higher than what this explainable AI model has predicted for the energy use during occupied hours. And we can really highlight that that is where our problem is. It's not in overnight setbacks. We don't need to look at thermostat settings necessarily, right? Instead, we need to look at something else that's going on in this particular system. For those of you that are really curious about what actually happened here, this HVAC system had a variable speed drive on the compressor, and it got bypassed. And so now you've got your compressors running full speed rather than varying speed, which saves energy. And just as a reminder, we've been really kind of focused on a single HVAC system or a single facility, but these tools as well can be utilized in a portfolio level. There is no need for us as energy professionals to spend our time analyzing what's going on with a system that is working properly. Instead, we really want to focus our efforts on the places that are going to make the most impact. And you can really start to look at this on a portfolio level, and again, find those black sheep on the systems that aren't performing the way that you would expect them to. Now, I want to go in because we touched on anomaly detection when we started to look at what was happening throughout the day, overnight hours and daytime hours. And that's something that these tools can really allow us to do on more scale as well. So we saw that on an HVAC system. And so now I want to bring you to some data that's a whole facility. This is still a fast food restaurant. And what we're really looking at in this particular view is whether or not the facility has good overnight setbacks, right? And so this could be similar to Jan's example where it's because of an HVAC system. It could be anything that's running overnight in this facility. And so these models now give us a prediction for every hour of the day and every temperature what the energy use of the facility should be. And if we go to the blue bars at the top of this, you can see that it's highlighting that there's something going on. And what we're looking at here, in this case, our model is now in red and our actual is in blue. And so our measured energy is greater than the prediction overnight. And we can start to point this out as it happens every night. This particular case, very, very common. So this is a fast food restaurant, and they had a new closing manager that started. And so you can tell which nights that new closing manager closed and wasn't quite on the shutdown procedures that were proper. And the nights that we don't have that anomaly detected, it's likely that new manager was not the closing manager during those nights. And so you can really start to see things. In this case, it's not only an issue with equipment, but it's actually occupant behavior that we're pointing out in this case too. And even with anomaly detection, this isn't something that you've got to kind of like dig into each individual site, each individual piece of equipment if you have sub-meter data. Really, we can look at this at a portfolio level as well. So there's really no anomalies that are going to remain undetected, even if you have a really, really large portfolio size, because we're using this explainable AI to really point out the things that we need to know. And also to prioritize those things. So we can start to look at the duration of those anomalies and how much they cost. So that now as an energy professional, you've not only highlighted where the black sheep are, but you can quantify and prioritize based on how much it may save the facility. You can really focus now on finding the root cause of what the issue is and communicating those specific action items to the people that can really impact and fix the things that we find. And with that, I will hand things back to Jan.
Yeah, thank you, Allison. And I just have a concluding slide here. So first of all, I would like to emphasize the importance of data-driven decisions. This explainable AI can provide you some actionable insights, like things that can help you to detect more energy savings opportunities and focus your attention to the problematic parts. Like compare this with kWh per square meter per year. So this is the most commonly used metric. It usually does not help much in showing what is the root cause of it, but here you may go further using just the main meter data and being able to provide some useful information for technicians that will handle investigation there. The second point is related to scalability. We did not discuss this much in the previous slides, but what is important here is that due to the fact that you just may start with the main meters, allows you to focus on very small buildings. Actually, these fast food restaurants are not consuming much, just a few dozens of megawatt hours per year. And it's much easier to focus on a big office building, and there are usually more interesting energy savings opportunities. But this kind of it allows to analyze also these smaller buildings. And let me give you an example. Like because we are also focusing on, for example, when we are analyzing bank branches, there could be small branches with just the 20 megawatt hours per year of energy consumption, and we still have this overview. And you may find something like 500 kWh of potential savings. And is it worth the visit, like jumping into car and riding to another city? Probably not. But in many cases, you just can fix it by changing some schedule in building management system, and then it's definitely worth it to do that, because within a few minutes you save half a megawatt hour, and it's quite nice achievement. And therefore, since it's so easy to have these insights, you may focus also on smaller buildings and do that in scale. And the last remark here is more on the philosophical side of this issue, because sometimes we may hear these things like AI will replace humans or experts, etc. That's not true here. Actually, it will not replace them, but it will make them more efficient and make them focus on where the skills that they can provide are used most efficiently. And I really like this example that Allison just said, like the new manager. This is something where you really need someone to talk and to interpret these insights, but you may have AI as a tool that focus your attention on this particular issue, and you may spend your time on solving it and make your time more efficient. So this was the last remark here, and thank you very much for your attention. And if you have any questions, we would be happy to answer them.
Thank you so much, Jan and Allison, for the insightful session. AI is clearly transforming energy management. So now the portal is open for everyone to drop in their questions using the Q&A button. To start off with, I would like to start off with this question that says, how much data is required to begin modeling?
Okay, so usually it's suggested to use 12 months of data. And the reason is simple, because it covers all the seasons within the year. So the building is exposed to different temperatures, different regimes, and it will cover all the situations that you may find when predicting. So if you limit yourself just to summer data and try to predict winter consumption, the model will probably fail. So we propose to use 12 months. This is also part of the MNV guidelines.
Got it. Thank you. And then I see another question by Sridhar. It says, what is the difference between red screen, M&V, and this digital twin?
I'm sorry, I'm not aware about the red screen. Allison, can you comment on that?
I am not familiar with red screen either, actually. I haven't utilized that tool for MNV before.
Got it. Let's move on to the next question that says, how was the AI model created?
Yeah, it's a complicated question, but in a nutshell, you need some algorithms that will allow you to feed in data, measure data, and this algorithm will consume the data and try to find out the best setting of parameters of the model to minimize the prediction error. So similarly to these large language models that are just trying to minimize the error of the prediction of the next few letters, in this case, we are usually minimizing some error of a prediction given the training data. And there are various numbers of different algorithms that can be used, but in general, they are using the same principle. In our case, in these examples, the TOWT or our model is based on regression models. And in case of TOWT, it's formulated as an ordinal least squares optimization. In energy twin model, it's quadratic programming with constraints to be more specific.
Got it. The next question is by John that says, how to incorporate energy efficiency measured data into forecasting model?
Actually, this model is driven just by the measured data. So we just, or in general, if you're using these techniques, you do not tune something like energy efficiency. You just take this baseline and say, these are the training data, and try to learn these relations between energy consumption and different factors that do influence it, like weather, like time of it, like occupancy, etc. And that's it. So it's more about selecting the appropriate baseline period, as Allison pointed out in her part, and model somehow captures this behavior, and it's used as a baseline. And then when predicting, it provides this, for example, if you are focusing on TOWT or some model that has weather as an input, it provides weather compensated or prediction that takes into account the current weather conditions and provide the expected energy consumption. So it's just about the feeding the data and not tuning some parameters like efficiency of a building or thickness of wall or some heat transfer parameters.
Yeah, I think, Jan, too, if I could add something to that, when you have that baseline model, if you have a prediction or an estimate for how much a particular energy conservation measure is going to save, at a very high level, you can create yourself a key performance indicator that might say baseline model minus 20%. I think you can go even a little bit more in depth, similarly to what Jan's model was with the cooling setback, where it was 80% versus 30%. And if you have some sort of target, creating a simulated model from that target can be a way that you can sort of compare your baseline model to that simulated model as well, if you kind of know what to expect with that energy conservation measure.
Interesting. There is another question that says, let me actually filter out this one. Yeah. How is it possible to create a similar analysis for a hospital energy performance, and how much would it charge for doing it?
Yeah, it's possible to do that for a hospital. Actually, we prefer to do that for office buildings or buildings that do have setbacks, because there is a lot of potential for energy savings. in case there are no setbacks like hospitals or hotels, this is not an issue. But again, there are different things that you can focus on. We have been doing this several times, and yeah, there are different things like detecting anomalies, comparing to some baseline, etc. That could be still quite a lot of insights provided. I will skip this. How much we charge, because it's educational webinar. Please contact us directly.
Perfect. The next question is, will this technology provide the different, I think we got this one. How would you import data into your platform? Are you able to directly import data from utility companies' database?
Yeah, that's always an issue. And actually, we have several ways how this could be handled. You have seen some screenshots from SkySpark. So this is a software that we are using, and there are different ways how data could be imported. And we also have a platform where you can upload the CSV or XLS file. Actually, in a follow-up email, you will receive a voucher, so you will be able to try it by your own. And we are looking forward to implementing some of the utility APIs directly in order to be able to read the data directly using utility API or other services.
Yeah, if you have another way, if you have an Energy Star Portfolio Manager account and you have your data there, a lot of times people for utilities that have automated data into the Energy Star Portfolio Manager, that's another way that we can look at collecting data, because that's something, especially if you're looking at regulation programs in states and cities around, a lot of the utilities within those territories are starting to have direct connections to that Energy Star Portfolio Manager.
Interesting. And one of the questions that we have on the sample list is, in one of the slides, you mentioned 26% of saving. Are such results typical, and what steps were involved in achieving them?
So I'll take that, because I think that's about the implementation. I think that across buildings, small buildings and large buildings, there's a lot of room for energy savings that's out there. I think that typically something in the neighborhood of 15 to 30% is probably a good target. And every building is going to be a little bit different, right? Depends on the equipment that's in it, how it's occupied, what people are doing. On the example with savings, that was really looking at the whole building and putting in controls. So it was targeting HVAC systems, including the exhaust hoods and ventilation, lighting, and refrigeration systems. So in that case, everything but the cooking load, since it was a fast food restaurant. But I think that's pretty typical of opportunity that's out there generally in buildings. 15 to 30% is typical.
Understood. To all the participants, we can see the questions coming in. Some are very centric to the product. We'd request that if you have any questions related to how AI can, in fact, help your energy management planning and stuff like that, please do go ahead and use the Q&A button. The next question that we'd like to take up is, can you elaborate on how the explainable AI is used to understand the relationship between inputs and prediction? Is it based on LLM?
No. It's not based on LLM, because LLMs do have different purpose. They are just for predicting words. So they actually can help you when working, when trying to develop these tools, these models. And yeah, I have to say, I'm just amazed about LLM every day. And it really can speed up process building that. And but you should need some of these existing tools. And I can suggest to use Python, since it's the most popular language for machine learning models. And you have enormous amount of very nice software packages, easy to start, lot of tutorials. So there are different ways how to jump in. And if you want to use some of these not black box models like these neural networks and so on, there are these, for example, these open source packages that have been listed in the slides, and you can just start with them using Python or R.
Got it. The next question is by John, and it says, in case of unsupervised learning, how do you separate the contribution of energy efficiency measure from the rest of the data?
I did not point it out, but we are using, in this case, we are using supervised learning. So how it's interpreted here is like that these input data that are fed in are provided with this expected output. So it's used for training the model. So what's going underneath is the good practice. Actually, it's not part of MNV specification, surprisingly, but in machine learning work, you usually split your data set into training and validation set. So you train your data and you then use, I don't know, 20% of data that you left out from training to validate your model. And this is a way how you use the supervised learning in order to be sure that it's providing these predictions in general, not just for the training data.
Perfect. We have 4 more minutes to continue the Q&A session. The next question is, do you store the data for ML models outside of infrastructure?
That's a tricky question. It depends. Actually, it also depends on the complexity of our model. So we did not discuss these monthly models, but it's questionable if it's AI or not. But also this degree-based model or change point model is also example of regression modeling, and you have just a few parameters that you can write down on a piece of paper. So it could be as simple as this. But for example, this TOWT or the model that we are using do have hundreds of parameters. So you need to store them. When we are working with regression, random forest or neural networks, it could be megabytes of data to store these model parameters. So you need some storage. And actually, we are using AWS infrastructure in order to be able to comply with different requirements in terms of where the data are stored and how safe are they.
Got it. While we wait for more questions, we just have 2 more minutes. I would definitely like to understand a generic question. So for companies just starting with AI, what's the most practical first step that they can take?
Actually, I would suggest to make a review. What are these possibilities? How you should grab this AI, not just to jump into some hype, but focus on where are the potential practical impacts, not just making some prediction, but knowing what you would like to focus, how you want to handle. I can give you an example, practical example from our collaboration with Allison. We have been talking a lot about energy savings, but you can also try to focus on peak demand reduction. And it's a completely different story. You may want to focus on short-term prediction in order to provide some peak shaving, etc. So there are different ways how this could be utilized. And I would suggest to start with this, making sure that you are using it in the field where it's most beneficial for you.
Wonderful. I think that's all the questions that we received for today. Well, thank you so much, Jan and Allison, for the great presentation and discussion. And thanks again to our sponsors, Energy Twin. That's a wrap for today's webinar. And Jan, if you could just move to the next slide, please. Perfect. So CX Energy 2025 is where AI also meets energy innovation. Explore its application for distributed energy resources and building system optimization with different sessions focusing on that. Registrations are now open for CX Energy with an early bird discount of $100 if you use the code SAVE100. So head to cxenergy.com for more information. And again, thank you so much, Jan, Allison, and Energy Twin for such an insightful presentation today. You all have a good day.
Thank you very much.